Hello, I'm Ethan Roman, and this is my Faraday's Law Lab 5 presentation. So what is this experiment? We're essentially dropping a magnet through a tube of conducting aluminum foil as a real-world application of Faraday's Law. And the physical principles at play besides Faraday's Law are the Biot-Savart Law and Newton's second law. Here are my data measurements and observations. For my data, so we did 5 runs, timing how long it took the magnet to go through the tube, and there was an average about 0.46 seconds, and the simulation time in the code showed 0.917 seconds, and that's likely due to errors and the fact that our aluminum foil wasn't very thick. I scrunched it up a little bit, and it likely hit the tube and did not fall perfectly. In terms of measurements, the width of the foil was 0.001 meters. The inner radius of the tube was 0.0155 meters. The length of the tube was 0.31 meters, the radius overall was 0.0165 meters, and the mass of the magnet was 0.0241 kilograms. And the time to fall under gravity theoretically would be 0.25 seconds, but when we measured it, it was around 0.28 seconds. And this is likely because we do not have the correct mass of the magnet, but just a relative guess. For the observations, the foil width was likely too thin, resulting in a smaller induced magnetic field, which is why our time was so small. And it was difficult to get the magnet to fall straight through the tube, and it jostled around a little bit. All right, here's my coding. Here on the top right, it is showing red, which I'll go into in the next slide. This is my velocity versus time graph. So as you can see, the magnet reaches essentially a terminal velocity as this is the portion where the magnetic force and the gravitational force become equal, since there's no acceleration. Velocity is constant. This is what I thought the most important part of the code was, which is the function for the flux, the magnetic flux, and we reference this later in the code in our while loop for simulating this drop. Okay, interpreting the simulation. The blue part here, so when this turns blue, indicates counterclockwise, while red would indicate clockwise. I can tell by the changing the sign of the magnetic moment. So when it's negative, which means the magnetic moment is pointing in the negative z direction, the current should be moving counterclockwise. The color that shows when the magnetic moment is negative is blue. The dynamics of the system does not change when the magnet is flipped. The only thing that changed is the direction of the current, but that does not change the overall dynamics of the magnet. The computational model calculated a much longer time in the tube than we observed in our real-world experiment. The computational model can be made more accurate by decreasing the time step, getting as close to 0 as possible. The graph tells me that the force of gravity and the magnetic force became equal and opposite for a duration. All right, in conclusion, if the resistivity were reduced close to 0, the magnetic field resisting the fall of the magnet would increase. The magnet would move much more slowly down the conducting tube. If whole slots were cut into the tube, the magnet would fall faster through the tube. This essentially deletes the rings from the model, and decreasing the number of rings decreases the opposing magnetic field and force. Thank you very much. That's the end of my presentation.